Okay, it's 7:05. Good morning, everyone. My name is Graham Helfrich. I'm in Calgary, Alberta, and we're going to be learning a little bit about nodal analysis today. And it's also called wellbore optimization. The whole idea is production engineers. One of our jobs is to keep the well's production as strong as it can be, or if the production's gone down, do something mechanically that we can with the wellbore, whether it's changing tubing, lowering the pressure at the surface, putting some sort of artificial lift in to get that production rate back going. And so we're going to be looking at some software ways to try to recreate and predict and anticipate potential solutions to getting the rate back on track. So that's what we're going to talk about today. So I'll give you a little hook. I'm trying to get you hooked about why does this even matter? What are we going to be learning today? One thing we're going to learn is how to get the daily bottom hole flowing pressures for every well. Okay, and we actually did a paper about this year to figure out how reliable are these predictions of bottom hole flowing pressure. Ideally we'd have a gauge down to the bottom of the hole, but I think less than 5% of wells, onshore wells in North America have a gauge. So how reliable are these predictions of bottom hole flowing pressure? And I'll share that paper with you today and as a follow-up. Now for wells on gas lift, we often have gas lift valves, and ideally we want to be injecting at the bottom valve because that's where it can do the most good to reduce the hydrostatic load and lower our bottom hole flowing pressure. But are we really at the bottom valve? So we're going to learn how we can use some valve details, input them, and predict which valve are we actually injecting to historically. We're going to be learning about inflow performance relationships, which is really what is the potential for the well to deliver rate at different bottom hole flowing pressures, and comparing that against the tubing hydraulics, which is sometimes called a VLP, vertical lift performance, or PPC, tubing performance curve. Basically, these relationship between the reservoir potential and the wellbore hydraulics. So we'll try things like casing flow versus tubing flow, gas lift scenarios, and this is probably one of the most familiar parts for any production engineers. Grading calculation. So this is really where we're going to be taking our surface pressure, figure out what is the flowing pressure all the way through the wellbore, all the way to the toe, and asking ourselves, is it mainly friction that makes up the pressure loss in the wellbore, or is it gravity or hydrostatic effects? Now, Devin, I think it was Devin, approached us last year with this idea of something called the gas lift curve. And the whole idea is to have a relationship between what your oil rate or liquid rate is out of the well against what your gas lift rate is that you're injecting, right? To have the whole spectrum of different gas lift rates and show what the responding liquid rate would be. So we're going to look at that. We're going to figure out, what is our theoretical maximum liquid rate we could get at a particular gas lift rate, and compare that to where we're actually operating today in terms of a liquid rate and gas lift rate. And then, of course, that means we can quantify, is there an oil rate we're leaving on the table that can be achieved through a change in a gas lift rate. And we're even going to talk about over injecting gas lift, which I've seen at a few operators when we look at their wells. So that might be another opportunity if you can dial back or even maybe turn off gas lift completely without harming your liquid rate. We'll explain what does that even look like? How do you find wells like that? All right. Now for gas wells, liquid loading is always a topic that's valuable. So we'll look at how do we check if or when a well has liquid loaded. Now at the very end, I'm going to give you a little preview about what's coming next for nodal analysis in Whitson and some other ideas that we're working on for the future as well. Okay, so hopefully that's a little teaser, and you guys are just totally fascinated. I can't wait to jump in. All right, so a bit of a more detail about what we're going to do. The course, I think we have 4 hours allotted. It might only take 2.5 hours, honestly, so that could give you some time back. We're not going to be focusing deep on theory today. We're going to be more going through workflows together. We're all going to be following along, doing the same steps together so that you can repeat this on your own wells. Later, if you're for some reason you don't touch the software for a few weeks and you want to get back into it and learn this again, if you go into our help file, and I'll show you how to get here, there's something called a Nodal certificate, which is going to go through very similar steps to what we're going to do today, but you can just do it at your own pace. And then if you do want to learn about the bottom hole pressure theory, all those correlations, there is a video available here. So I'm going to send everyone these slides. I think you might have even got them in the last 12 hours from Matthias. So the theory about all this is available at another recording. All right. Now, something really important to emphasize is our technical support. So everyone you see here, these are Whitson employees. Everyone here is an engineer. and our average response time is 2 minutes. And feel free to test that out. So you just email support@whitson.com. And so after the course, if you're stuck, if you forget one of the steps that you learned today, if the result isn't quite making sense to you, just email support@whitson.com and we're going to be in touch with you right away. So make sure to be in touch with us. All right. So the agenda here, first we're going to look at a gas well. We're going to start kind of simple. And we're going to say, how do we calculate those daily bottom hole pressures? Is the well liquid loaded? There's this technique called the flowing material balance, FMB. And if you're a reservoir engineer, you may have heard about this or used it before, but we're going to actually do it today as production engineer. And the whole purpose is to figure out what is the current of the well without doing a shut-in. Okay, so that we're going to use the flowing material balance to figure that out, and we'll look at that. We're going to create our inflow performance relationship, our VLP curve for this gas well, and then we're going to compare things like what if we flow it just up the casing? What if we add compression? What if we install large tubing? What if we install small tubing? So we're all going to go through these exercises today for this gas well. The next well is going to be an oil well that's on gas lift, and we're going to say what gas lift valve inputs, what depth are we actually injecting to for gas lift? What are the daily bottom hole flowing pressures? We're going to do the same flow material balance to figure out what is the current reservoir pressure without a shut-in, and then we're going to do our IPR VLPs and a gradient, and we're going to do this really cool thing called the gas lift curve. The whole idea here is we're going to figure out, are we leaving oil rates on the table for anything that we can control with a well? Okay. All right. So with that, we're ready to get started. I should say at the top of the hour, we're going to take a 10-minute break. So just be prepared for that as well. All right. So we'll start with the gas well. Now, if you haven't already, I want everyone to go to courses.whitson.com. And I should mention something else too. My colleague Matthias is here. So if something's not making sense, or if you can't get into the software, use the chat window. Just type your question into the chat window. And Matthias, are you going to be along for the course?
I'll be support. Tech support.
Okay. Thank you so much. So yeah, just type any issues you're having into the chat window with the Teams meeting, and Matthias will get back to you. So we're all going to go to courses.whitson.com, and you'll be prompted to enter a username and password. So your username is just the email that you registered for this course with, the email that you sent to Matthias, and then the password is here on the screen, capital N for Nodal 2024 exclamation mark. I'm going to give everyone a minute or so just to courses.whitson.com. Okay, 20 more seconds, and then we'll all get in there together.
And for Heidi, I sent you a email now with one thing that worked, at least on my end, and I think it's because I think we try to add both your Diamondback email and your Endeavor email, so just messed things up. But I think that should work.
All right, so when we go to, we should be basically seeing that we're looking at the Whitson software now. If you haven't already, we're in the top left where it says fields, and I want us to type in the word Nodal here, and we should be getting this one here that says training. I'm just going to I'm going to make sure that we can all access this because I had it private before, so I'll make sure everyone can access this. There we go. So and again, under fields, I'm just going to type in Nodal, and we should be getting this one that says Nodal course October 2024, and we can all click on that box or that field called Nodal course October 2024. And when you get in here, if you don't see a project that's called main, I want you to click refresh on your browser, because up until now I had this kind of as a private project, but I just made it what's called company wide, and we'll explain that in a minute. But I want you to just click refresh on your browser until you see main company wide, pretty much what I see on my screen. Okay. So again, refresh on your browser to see this. So I want everyone to click on the project here that says main, and in here we see a gas well and an oil well. So we're going to click on. All right. Now, before we get started, I want to emphasize, Whitson is a multi-user software, meaning we are all looking at the same well now. Now, do you think if we all tried to interpret this well at the same time, we might be stepping on each other's toes? And the answer is yes. And so the way we solve that is up at the very top where you see my mouse, it says scenarios. We are going to make our own little scenario, which is going to be like our sandbox that we can play in and analyze this well without messing each other's work up. So under scenarios, click on the drop down, and it wants to say add new scenario and type in your name. Now there's a lot of people on this, so some of you might have the same name. So maybe put your first name and last initial, or your whole name if you want. Now you'll notice that there's an option below that says make this company wide or make it private. And so what this means is if you're to make this scenario private, you are the only person at your company who can see your interpretation that we're going to do. All right. If you make it company wide, it's as it sounds. Anyone else can see it. Okay. And you can change the status of these later. So whatever you want to do, you can make it private or company wide. It doesn't matter, but just type in your name for scenario. and then save. All right, so we should see under scenarios at the top, it should say your name. If it doesn't say your name under scenarios, go ahead and make it say your name so we know we're on that. So now we see that there's a bunch of people here who've made their own scenarios, and that's just going to let everyone independently look at the well and then do that. Now, as a bit of a preview, let's say you made your scenario private, but later you want to make it company-wide. What you would do is at the top, you can say view all scenarios. And then if you scroll way down to the bottom of the screen, by the way, you will not see each other's. I only see private because I'm with Whitson support. But if mine is here, I don't even know if I made mine company wide or not. I did. Okay, so you would just go way over to the far right of your row, and you would say either make private or make company wide. So that's where you can change the status of that. And if you think that you have the best analysis, you can even make your scenario called the main scenario. Okay, so again, this is just how we can make copies of an interpretation to independently look at the well. All right, so as long as your scenario still says your name at the top, we can continue over to the far left side. So the workflow generally works from top down to the bottom. Now, because we're not going to be doing, any defits today, we're not going to be doing much rate transient analysis. We're just going to be picking some of these steps for nodal analysis. And we're going to start with PVT along the top here, okay? So we can click on PVT on the top left. And again, still make sure it's still your scenario name in the top right. It should be. Okay, so under PVT, we see this kind of beaker over here. And then where my hand is right now, there's a little square box, and we can click on that square box. So most engineering software I have used, when it comes to compressibility or viscosity, anything PVT related, those other software used correlations typically. But Whitson, if you didn't know, we're kind of famous for being PVT experts going back 30 plus years. And so we use an equation of state built right into your Whitson software. Now, for a dry gas well, it's not super important, but once you get into some liquid rich wells, like the oil well we're going to look at next, that's where this equation of state model is really useful. Okay, so again, we're under PVT. We click on this we call it a card. It looks like a little beaker, and we're going to click on the square box in the top right. Now, this is where we kind of initialize the PVT. Down in the middle, right now it says method GOR. Now, this is a dry gas well. It doesn't have a GOR. So we're going to use this drop down where GOR is, okay? And we're going to pick dry/wet gas. And we're going to type in a specific gravity over here of 0.65, and then you can say save. The EOS, the equation of state, is running on the cloud right now, and it makes this phase envelope. Now for dry gas, it's not that interesting. We'll look at this a bit more closely once we do the oil well, okay? So that's the PVT step. Next, we're gonna go down to production data, which is one more step down on the left, all right? So we'll do a little orientation here for the plots and the scales and all this kind of stuff. So in red, we have the historical gas rate, and if you mouse over, we see the initial rate for this well was quite high, 30 million cubic feet a day, and then it's been declining down to 6 or 7 million cubic feet a day more lately, okay? Now, on the bottom, we're looking at our dates in a calendar date, but you can also toggle, there's a little date button up in the top left. If you click that on and off, it'll basically show cumulative time, which is about 2 years, or date time, whatever you want to pick here, okay? We also have some casing pressure in gray here, and we have our water rates. Now, if you want to toggle some of these lines on and off, there's a legend at the very top, okay? So if you just single click on anything in the legend like that, it'll toggle that data set on. Now, what if I only want the gas rate to be shown and everything else to be removed? Well, instead of single clicking everything away, there's a shortcut. If we go over gas and we double click really quick on gas like that, that will cause it to be the only thing that's shown, all right? And then you could turn things back on again if you wanted. So again, single click is like a toggle, and double click causes only that data. Now, what about zooming? Okay, well, my favorite way to zoom is to draw a box. So if I were to zoom in on part of this gas right here, I'm just gonna hold my mouse button down, and then I can even do that again if I want. I'm going to draw a box around what I want to zoom in on, and then I let go. And how do you zoom back out? Well, I just double click anywhere on the white part. I had to do it twice. I'm not sure why that happened, but I double click on the white part of the plot, and it'll reset the zoom. It should get back out to this. Now, you can do the same thing. If you don't want to double click, there is a button up in the very top right that says reset zoom, and that should do the same thing as double clicking. Now, since this is a web-based application, there are some tips that can help kind of improve your experience, and this has to do with zooming in or out. So by default, if I'm zoomed in at 100% of my zoom for the screen, what I mean is I'm holding control and hitting plus or minus. And you can see in the top right of my screen, it says 80%, 75%. I'm hitting the control minus button. And so I find that the best zoom is about 80 or 90%. So if you want to try that, just hit control and then minus or plus with control. And I'm going to leave mine at, I think, 90%. Now, the last thing about the production data is if we scroll down to the bottom, we see that there's a table of our historical daily rates and flowing pressure. All right, that should match what's on the plot above us. Now, we're all in our own scenario, which means we can kind of make our independent interpretation of the well, and that's true. But there's one thing that is common among all of our scenarios, and that is the production data. The production data is going to be honored and be consistent and cannot be different between our scenarios, okay? All the interpretation of it can be, meaning we can do different PVT, different bottom hole pressures, different nodal analysis, but the raw production data has to be the same. So you notice that I'm under the scenario called Graham, and I can't edit. I can't change this production data. The only way to do that is if someone was in the main scenario, then the production data could be edited there, and it would therefore change for all scenarios. Okay, so in short, the only thing that is the same or consistent between scenarios is the production data.
And that's just a quick comment there, Graham, that's very helpful for most of the companies, 95% of the companies that we work with that have a database connection or are connected to the API where they're updating their production data on a daily basis. So you can basically create your own analysis or your own scenario while still getting the production data updates to the given well. So that's kind of the main purpose of the connection to the production data.
And for everyone, that was Mo, our COO, who recently moved to Houston, Texas. Yes.
I had a question about the plot. Just as an example, the water gas ratio, it kind of drifts off the bottom. Is there a way to adjust, say, the units for water gas ratio on a plot like this, to where it's like 1,000 stock tank barrels per million, so it shows up in a better position on the plot?
Yeah, good question. So just to reiterate what you talked about, we've got this little water gas ratio thing, but it's kind of not as useful as it could because of the scale. It's just kind of squished down there. And if we were to move it up, all of these axes are kind of tied together. And so, we're actually we're doing an overhaul of this plot right now where it can be more customized, where you can kind of detach water gas ratio, have it on its own scale, change the units more. So what you're describing is in the works, and it's in the works right now. So, but at the moment we can't really do anything about that.
Thank you.
The workaround, we can talk about this later. You could recreate this plot down in something called the comparison plot, and you could have more control there. But we're going to be working to make that same control available right here. So last thing for zooming is the if you notice, let's try this. I want everyone to go up in the top left of the plot until you see a double-headed arrow, like this little arrow where the arrow is going up and down like that. And if you see that, you can hold your mouse down and drag down and then let go. You can even do that again if you want. Double-headed arrow, drag down and let go. That's how you can basically change the scale on the y-axis, or if you want to do it on the x-axis, just go to any corner until you see the double-headed arrow. Then you just hold your mouse and drag. If you want to get back to your reset zoom, just double-click. And I have to do it twice there. But the one I use the most is honestly the drag. This is the one I use the most often. I just draw a box like that. So it looks like I'm having a little thing with the reset zoom where I have to double click more than once. So we'll look into that. But that's about it for zooming. Okay. All right. Let's look at our bottom hole flowing pressure. So down on the far left, we're going to say bottom hole pressure is right here. So let's investigate what does this wellbore look like a little bit. So there's a pump jack symbol up here, and we're going to go to the right where the little square is, and we'll click on that. So these are where we have the wellbore details. Now, the first thing we see is the deviation survey, MD and TVD. It's just in a table. Often people will connect to WellView or WellEase, wherever their wellbore descriptions are, and that can be automatically populated in here through an API connection if it's not already. If you want a little preview of the wellbore, we can click on this little symbol above the table right here, and that shows us a little preview of this wellbore. Okay. Up in the top right, we're going to click on well data right here. We see a bit of a description. So we have the casing diameter, the casing depth, and notice that there's no tubing data, and the flow path says casing. So this particular gas well has no tubing. It's just flowing up the casing. So that's good to know. We can actually close out of the screen either X or save, and we are going to say calculate bottom hole pressures in the very top left. We can click on that. Okay, so what just happened was all of the daily rates and the surface flowing pressures were converted to a bottom hole flowing pressure, and by default we calculate down to the top perf. So that's the depth that we are calculating to. There's a bunch of colors below. Well, why is there more than one bottom hole flowing pressure? The answer is because we have different pressure loss correlations available, and it's good to consider them all to see that there could be a range of bottom hole flowing pressures depending which correlation. Now, because this is a gas well with a little bit of water, the range of these bottom hole pressures is pretty small. Like, they're pretty tightly grouped. We're going to notice next for the oil well, these results spread out a bit, but for gas wells, they're usually pretty close. Now, for anyone who's analyzed a lot of gas wells, you probably use gray most often, or maybe something else. I see gray the most commonly used for gassy wells. And I want to share a quick paper with you guys, and I'll make sure you get a copy of this after as well. We have some great partners, Whitson, and these companies here provided us with, I think it was 600 gauge data sets, downhole gauge data sets with daily downhole pressures. After sifting through them, we narrowed it down to about 400 data sets that we really trusted. So I think over 300,000 data points overall. And the whole purpose was, if we have a measurement of the downhole flowing pressure, let's compare which correlation is the most accurate against the measurement. Fast forward into the results. These are the 4 correlations that we use in Whitson. And if we look at Hagedorn and Brown, for example, if all of the red dots were along the 0% line, that would mean that the correlation perfectly matches the measured gauge pressure. But Hagedorn underpredicted the pressure by about 5%. The W and G one here overpredicted by about 5%, not bad. But Beggs and Brill was the worst, and it overpredicted in this study about 16% what the bottom hole pressure was, and Gray underpredicted by about 12%. And I guess I was the most surprised by Gray, especially up in the high GOR range, because I really have used it a lot for gassy wells. But my takeaway from this is I'm personally mainly using Hagedorn and Brown and the W and G one. Now, this is not a comprehensive study, but it was a good one. And I'll make sure everyone gets this paper after. All right, we might even paste it in the chat window if someone gets a chance. All right, so for this particular well, the grouping is pretty tight, so it's not going to matter too much which one we pick. But I think for this one, I'll pick the W and G one right here. So I want everyone at the very top. There's a drop down. It says bottom hole pressure to be used in calculations. Once we move forward here with our analysis, we need to pick one of these methods. Let's pick the W and G1 here from the drop down. Okay, now let's look at liquid loading. Okay, so on the right where my mouse is right here, we can click liquid loading plot. So what we're looking at here in red is the well's actual gas rate, 30 million a day down to 7 million a day. The blue line is the critical lift rate according to Turner. And so, the way I used to describe this, I would have a hair dryer, and I have a ping pong ball. You turn it on, and the ping pong ball is just suspended in the hairdryer's wind, right? So we have 2 effects happening. We have gravity trying to pull the ping pong ball down, and then we have wind is causing drag on the surface of the ping pong ball trying to pull it up. And when the ping pong ball is just sitting in the same place, you have this equilibrium where those 2 forces are equal, right? It's not going anywhere. And that's what liquid loading is like. These water droplets, we're usually trying to evacuate and sweep them all the way up to the surface, but what velocity do we need? What gas velocity is needed to successfully do that? Well, that's what this critical velocity or Turner velocity is about. It's very similar to a ping pong ball. And so, the way we convert a velocity, which is really what we're truly calculating with that drag on the liquid droplet, is we look at the cross-sectional area to flow, which in this case is casing diameter, and we can convert the required velocity to a rate once we know the cross-sectional area. So the minimum rate to lift liquids for this well today is around 6.5 million cubic feet a day. That's what Turner is about. And there's a drop down at the top. Coleman is just a 20% reduction from Turner. And there's these more modern critical lift rate methods called Nagu and Belfroid. Now what they do is they account for the inclination in the wellbore. And I don't know if you've tried these other methods. I find that they're quite sensitive, to a degree here, a degree there. They can make a big impact in the critical rate prediction. So I think I'm still learning the applicability of these more modern methods. So for now, I'm sticking with Turner and Coleman. And by the way, at the request of some of our Appalachian partners, going to be adding a liquid loading modifier soon for people who have field observations where you want to tune or change the critical lift rate based on what you see in the field. That's going to be coming very soon. Okay. So the short story about this is the well has not been liquid loaded. We're above the critical lift rate, but lately it looks like we're getting into kind of a dangerous flow rate where we could be liquid loading, and maybe it's time to install some tubing in the well, right? Okay. So we're going to move on to the flowing material balance. And just before we do that, I want to share a slide here. So what is an IPR? That means inflow performance relationship. It also goes by the term deliverability curve. Some people call it an AOF curve. AOF means absolute open flow. It goes by a lot of names, but it's really just the relationship between the bottom of flowing pressure and what the rate will be. So the way I like to think about it, and congratulations to anyone on the call who has 3 pedals on their car. You're a purist. I wish I still had that, but I'm going to talk about this pedal, the fun pedal on the right, the throttle. So when you push this, what's happening is you're opening basically a valve, a throttle body under the motor, and you're letting more air into the motor, and therefore it's making more power. Okay. And so looks like I missed a couple slides here. All right. So basically, we're basically making a relationship between if the well is shut in, we have this static average reservoir pressure in red, and then we take the rate that the well's actually flowing at today, which might be 150,000 a day, 1,200 pounds bottom well pressure. So this is like a known measurement point. And then often there's this thing called turbulence, which we just usually assume it's going to be 1, but this is the IPR equation. It's often called like a Rollins-Schallenhart or a CNN equation, and this is basically used to create this shape. Okay, so at any bottom of flowing pressure, what will the rate be? All right, so some of these these inputs are easy to get. Like we know what the gas rate is for the well. We can calculate what the bottom of flowing pressure is for the well. We've already done that. We usually assume a 1 for N, and we're trying to solve this C value, which is almost like the well productivity. The thing that can be tough to get is the current reservoir pressure. Nobody wants to shut in the well, wait for it to build up. And so we're going to be using this flow material balance technique to directly or indirectly estimate what this current reservoir pressure is. So this is kind of the equation to create this inflow performance curve. Now, once we're at higher pressure, we use a pseudo pressure, so there's like a slight modifier built in. So back in the Whitson software, we're going to figure out what the current reservoir pressure is for this well. Let's all go to the flowing material balance on the far left side here. Once you're there, you can click run, mess around with flowing material balance before in Whitson. You'll notice that there's a multi-phase option and a gas option. And you say, well, Graham, this is a gas option. We're using the gas option. I found that the multi-phase option is easier to make an interpretation in all cases. So I never use this gas option. I always use multi-phase because it's easier, even if it's a gas well. Okay, so the whole idea here is we're trying to look for the slope. This is our production data in blue, and the goal here is to say how big is the reservoir. And if we had a shallow slope like this, that means that we have a bigger reservoir that's saying 41 BCF. If we have a steeper slope, it's saying 11. And if we were to put a line right there, it says we're around 24, 25 BCF. Now this is gas in place. This is not EUR. This is what is the contacted pore volume? What is the contacted amount of gas we've seen with production data so far for the well? There's an auto fit button that works pretty well. In this case, it gets about 22.5 BCF. Once you guys have a slope that you like, we can say run. Now, one of the results that we get, and I'm just going to give you guys a bit of the next well is going to be more interesting with the FMB, but I just want to give you the goal to aim for here. Try to get around 24 BCF with the slope. We're trying to find the most shallow slope we can justify. If you bring this down to be the slope of this line until it says around 24 BCF, we're going to be in the ballpark. Okay, and if you're around 24 BCF, you can click run one last time. And we're going to be looking at this plot in the top right because ultimately, we're getting the original gas in place, but we want to know what the current reservoir pressure is. And that's what this plot in the top right is for. So we can expand this. So the dark black line is average reservoir pressure, and the gray line is the bottom hole flowing pressure converted from surface down to bottom hole, according to, I think, that correlation we used, right? So flowing pressure in gray, average reservoir pressure in black. So when this well was brand new, the initial reservoir pressure was 4,400 pounds. And as we produced gas, we know what we cumulatively produced. And so we can figure out, according to the size of what the remaining reservoir pressure is. through the well's history. And so as long as our original gas in place number is around 24 BCF, we should see our current reservoir pressure is around 1,800 pounds. Okay, why do we care about that? Well, when we do that IPR curve, this is a number we can use to help create that IPR. Current reservoir pressure is an input for our IPR. All right, so we're going to go down. Finally, we're going to go to nodal analysis down on the bottom. Okay, now we should be seeing this red IPR curve. The black dot, by default, it is just taking the most recent rate from the well's history and the most recent bottom hole flowing pressure from the well's history. So that's what the black dot is. Now, I don't know about you guys, but I see that my intersection point for my IPR, it's way up high, 4,500 pounds. But I know that my actual current reservoir pressure is lower. It's like we said, it's around 1,800 pounds, right? When we did the flow material balance, we estimated 1,800 pounds current reservoir pressure. So the way that we update that here is, you guys see there's a little calendar icon right here. I want us to all click on that calendar icon, and there's a vertical dash bar. You can grab that bar, you can drag it around, and this is basically how we sample the rate and the conditions that we want to use to make the IPR. So if we wanted like a past IPR, we'd go over here. But if we want the current IPR, I want us to drag this vertical line all the way to the far right, as far as you can go. And that's going to the reservoir pressure, 1,800 pounds, the flow material balance. So as long as you've moved this vertical line around to be close to the very end, we can click save. So we've got our current operating point, our current reservoir pressure up here. We can say create VLP up in the top left. Okay, so now we have our blue line, which is basically our tubing hydraulics, our tubing performance curve, our outflow curve. It's called a VLP. Notice that it is solid and then it becomes dashed. So that point where it changes to dashed is our critical. I think we're using Turner, right? So we're about to liquid load, right? We just have casing in the well. What are some ways to delay liquid loading? Okay, we're going to look at 3 different ways. Let's imagine that we have some compression available, or somehow we can lower the line pressure. So over here, the bottom left, it says casing head pressure. I want you to type in 300 psi and then create VLP. So down on the bottom left, casing head pressure, type in 300 psi and create VLP. All right, we should see VLP curves here. The black one is our original one, our current case, about to liquid load. And the blue one is if we can lower the surface pressure down to 300 pounds. And that's going to do 2 things. It's going to make our rate lower flowing pressure. It's actually going to delay liquid loading. So if we can lower the casing head pressure, we can remain unloaded all the way down to 3.8 million cubic feet a day. And part of the reason for that is when gas is very compressible, and so when we have it at a lower flowing pressure, the gas is expanding and the velocity of that gas is higher. So if you have 2 wells and they're both at 5 million cubic feet a day, but one is at a lower pressure, then the velocity of that gas is faster, and that helps drag the water up to the surface. So that's why we can have a lower critical. So let's save this case. In the top, it says save case, and I'm going to call it 300 psi casing head pressure, and then save. So that's one possible solution. If we have access to a compressor or a way to lower the line pressure, that is one way. Okay. The other way is to install some tubing on the well. Here it says new well configuration. Just to the right of that, there's a little square box, and we're going to click on that square box. Here it says new well configuration, and now we want to add some tubing as a what if. But tubing data, there's no tubing in the well right now. So we're going to click this little plus symbol where I am with my mouse. Okay. We'll just click it once. Again, if you didn't see that, I'm just going to back up for a second. New well configuration, square box, tubing data, plus. So for the depth, we're going to put 6,500 feet for our end of tubing. And on the far right of that row, it looks like 3 pancakes stacked on each other. We can click on that. This is our list of tubing sizes. So we're going to scroll down until on the left we see 2 7/8, and I'm going to pick the 6.4 pound. So find the row that I'm on. You can click on that. So 2.875. OD 6.4. The last thing we have to do is change the flow path here from casing, and that's it. Then we can click save and create VLP. Okay, so what we're seeing is if we install 2 and little bump in our end, we're going to remain unloaded down to, oh, you know what? I just remembered something, guys. We have to change the pressure, right? I think we were around 967 pounds line pressure. So I want us to type both of those numbers in here. For both casing and tubing, around 970 psi. Now, a quick mention, if we're flowing up the tubing, like we are with this new case, the pressure we enter in the casing pressure, it has no impact on the result. So it's really whatever the flow path is going to use that pressure input. In this case, it's tubing pressure. So make sure as long as your tubing pressure is around 970 pounds, you can say create VLP. So currently with casing, we're in the black line. If we install 2 7/8, we'll slightly reduce our rate because of some friction. We can remain unloaded down to 1.8 million cubic feet a day.
Graham, there's a question, a couple of questions. You could just help with those. So one question from Ethan.
Yeah.
If you could explain how to pick the flowing side versus the quiet side on the calculation. Yeah. And then he's asking, the second question is how you got that original pressure back if you just had to delete and press enter.
Yeah. Oh,
how
you mean like this pressure?
How you reverted to the original pressure there, yeah.
Okay, great question. So yeah, the first question was how do you use like quiet side? And when we say quiet side, we're talking about if we're flowing up the tubing, we're measuring the annulus pressure at the surface. You know, that annulus pressure can be converted down to the bottom hole flowing pressure, and it's called quiet side because there's no friction in the non-flowing side, but it's still a good way to calculate bottom hole pressure. So the way we could do that is when we're in our little wellbore description, you know, under bottom hole pressures, you know, if we were flowing up the tubing, there's an option here where it says compute through. So typically we will, like if you have a packer in place, for example, then there's no way you can communicate through the annulus to the bottom, right? But if there's no packer in place, your compute through option could be quiet side here. And so what that would do is take the annulus pressure, the daily annular pressure, it would do a hydrostatic pressure calculation down to the end of tubing, and then it would do a flowing pressure calculation from the end of tubing down to the top perforation. So the way that's how you use the quiet side pressure to calculate the bottom hole flowing pressure is in your initial wellbore setup, you pick flowing side or quiet side, okay? And the second question was, you know, we realized that we had the wrong lower 300-pound pressure in here, the zero pressure here. How did I just get this correct pressure back? Well, I cheated and I control-C'd it and copied it before, but the other way you can get it back is by going into the calendar icon here at the top like this, and you can just around and move it back to where you had it before, and that will snag the current pressure, which is 967 pounds. Okay, so but to be honest, I find myself doing that a lot, and I think we should consider some sort of little button here that says like, you know, apply from, you know, current or something, right? So
just refresh the values based on the current date. That makes sense.
Yeah, exactly. Yeah. So yeah, to repopulate these with the current pressures, there's a little improvement we could do with that. So I cheated and I had copied and pasted them to my clip because I anticipated having to reuse it again. Any other questions in there, Mo?
No, that should be all good.
Perfect. Thank you. Yeah, keep the questions coming, guys. Okay, so this is our 2 7/8 inch case. Let's save it. So save case in the top, call it 2 7/8, right? So that tubing is definitely going to help delay liquid loading at the slight cost of a rate just from friction, right? Let's try smaller tubing. Right here it says edit well configuration. We're going to click on this again right here. By tubing data over here, we're going to click on the triple pancake stack again, the little blue icon here, and we're just going to go down and find 2 3/8. I'm going to use 4.6 pound. So this row right here, the 2 3/8, 4.6 pound, create VLP, and we see that smaller tubing reduces the gas rate a bit. So smaller tubing, more friction, more pressure loss from friction. And so that causes the bottom hole pressure to go up, the rate to go down, but we can remain unloaded all the way down to 1.1 million a day. We're going to save this case, 2 3/8, save. And you're thinking, where did all these save cases go? Well, they're down on the bottom left. You can turn them on and off, and you can also make them visible or invisible with the legend as well, just like in all the plots.
Hey, Graham, one question I've had a long time with these, like when you're running tubing into a gas well like this, is if you run with no packer, like your casing side will be probably 1,000 pounds higher than your tubing side.
Mm-hmm.
Like, does changing that, backside pressure, does that change anything with the vertical lift performance, or is it only looking at tubing pressure?
So it only looks at the tubing pressure in this software.
So like if you put 0 on casing or 2,000 or 10,000, whatever.
Exactly. Like I could put 10,000 in here. Again, the flow path is the tubing in this case. This will have no impact on the VLP. Yeah.
Cool, thank you.
There's a couple of questions, Graham. There's a question from John. Maybe John, you could speak. I don't know if I understand your question about the liquid production. And there's another question from William. John, if you're available to.
Are we gonna talk about oil producing nodal analysis later? We're only going to talk about gas today.
Yeah, okay.
Yeah. In the agenda, I mentioned first well's gas well, second well's an oil well on gas lift. So we're just about done the gas well.
Okay, I'll bring up the question again when we go to the oil well. Thanks.
Sure. Yeah, I'll mention the oil well is going to be more, I don't want to say complicated, but there's going to be more, I don't know, for me, it's going to be more interesting. Yeah.
Yeah, the other question from William Graham is asking if you have to match the VLP correlation to the BHP correlation. So basically the correlation to compute the VLP here.
Yeah. Great question. In fact, I'm going to show you something like a problem that can be caused, but how to fix it. So here we go. So this is kind of this is like our current case, right? And we see that the black line goes through the black dot, so everything is beautiful. But sometimes you may come in here and it looks like this. You're like, what the heck's going on? Why isn't this black line intersecting with my current rate? And 99% of the time, the reason for that is because the correlation that we have picked here for the VLP, which is, in this case, I forced it to be gray. If we compare the bottom of flowing pressure that we used here, I'm using the W and G correlation. If the correlation we're using here is different than the correlation we're using here for the VLP, it will cause this mismatch in bottom of flowing pressures. And so again, 99% of the time, the solution is just to double check that the correlation used here is the same as the one in the BHP, pick everything up. And we're looking at maybe making some safeguards to make that less possible for people to do.
Yeah, great.
Okay. Any more questions? We're going to take a 10-minute break, and then we're going to get into this oil well on gas lift. Okay, I'll see you guys back here at about 10 minutes or 11 minutes after the hour, okay? Okay, we're back. I see there's a few more questions, which we'll answer here. For liquid production, can we overlay for lift choice selection? So when we say yield, are we talking like GOR?
Yeah, sorry that I wasn't here when we talked about the agenda and the gas wells and that we'd be moving on to oil. So I think that question is more applicable when we go to an oil well, because let's say we have a higher water cut well. I would love to be able to select, let me see my water cut. And even if I'm taking a 100-barrel total hit on the lift selection, if it's only a 1-barrel hit and I could keep that smaller size tubing for a longer period of time, that's probably the right choice, right?
Right. Yeah, because if you have a high water oil ratio, then the economics on that change differ than if it's all oil, I think. Another question was just about calibrating, some of these correlations to any gauge data. So I'll quickly show that this particular the gas well we looked at. I think I've got a gauge data here, like a gauge daily gauge data. I think it's synthetic for this example, but when we go to our bottom well pressure, we see that there's a black line embedded here, and that is the gauge data. So you can see which correlation may be closest to your daily gauge data. Like it looks like Hagedorn and Brown in red for this time series. But as we kind of look later time, the gauge data might be closer to maybe a different correlation. So the way we can use that gauge data, in addition to seeing which correlation is closest, is up in the top right of bottom well pressures, it says tuning. So with tuning, you can pick a row, pick a correlation. In this case, I'll do Hagedorn and Brown and say tune. But I think someone might have their mute off. If you could mute yourself, that'd be great. Thank you. So when you say tune for a correlation, it's basically modifying the liquid holdup, modifying the friction factor in that correlation against the gauge. And it's almost doing like a history match of the correlation to the gauge pressure. So now, if you say save and you recalculate your bottom well pressures, we would find that Hagedorn and Brown. We find that the Hagedorn and Brown, that correlation is basically closer to the gauge data. So that's a way you can leverage any gauge data to tune a correlation, and you can reuse that tuned correlation on other wells. So anyway, that's one of the ways we can do calibrating of the correlations. I think the question was more about a gradient survey, and that's something we're thinking about. Is this is one location, meaning one depth where the gauge is, but it's through a whole period of time. The other way would be if you have a flowing gradient survey, that's one moment in time, but different depths. So there's different approaches to calibrating a correlation.
And also one quick comment there, Graham, very good explanation. Also, you can use the same tuned correlation that you would tune here. You would use that kind of carries over to your VLPs as well. So if you have tuned it here and you go to your VLP, then the calculations of the VLP will happen with those tuning parameters.
All right, let's get into this oil well. So Up on the top left, it says wells. We'll click on that. And once you're there, you'll see oil well. We can click on oil well. And I want you to make your own scenario. Add new scenario and give it your name. Doesn't matter if it's private or company wide. All right. So as long as you're under your scenario for the oil well, we're going to go over to the far left where it says PVT. And we're going to click this little square box here. Now, this well has a GOR, 250, 300,000 scuffs a barrel. And we can basically, the job here is to basically observe the initial GOR for the well. This is going to help set the PVT up. It's going to initiate this equation of state model. And so for us, we can put it somewhere around here, somewhere between 250 and 300. Just for consistency's sake, why don't we all make it 280? We can type that down on the bottom. That way we'll all get the same results going forward. Okay, so 280, and we'll say save. So right now the equation of state is running on the cloud. The result is this. It predicts the phase envelope. It predicts the bubble point pressure. Now, this is a black oil well, but if we had a much higher GOR, it would classify it as like a gas condensate well or wet gas or all these different categories. So this is our phase envelope. And this is going to be used in our wellbore calculations. This is going to be used in the flowing material balance. This is going to be used everywhere throughout the software. Now, just for interest's sake, do you see the eyeball up here? If you click on that, it provides a prediction of the fluid composition all the way up to C30 plus. So the equation of state model built in here, it's available to everybody who has Whitson software, and it's called Peng Robinson. It's kind of a standard industry one, but I know a lot of people on the call are members of our PVT consortiums, which is where we've gone around and collected about $10 million worth of PVT reports from operators. And from that, we've calibrated or tuned an EOS model for the Eagle Ford. And we've tuned and calibrated an EOS model for the Permian, Duvernay, Montney, Bakken, Uinta, DJ. So a lot of you guys have these kind of optional EOS models that are calibrated, but everyone gets kind of the default one. So the results will be slightly different depending which of those EOS models you might be using. Okay. If you're not sure which one you have, just you can ask me, or you can always go to PVT and then click on the little EOS model button up here, and it will say Montney or Eagle Ford or Permian. Then you'll know which one you're using. Okay. Let's keep going with this well. So on the far left, it says production data. We'll click on that. So this well has only about 250 days of production history. I'm going to, if we double click on oil in the legend, double click on it, we see the well started around 1,300 barrels a day. Then there was a big shut-in, and then it came back online, and now we're around 600 barrels a day. The gas rate, 400,000 down to 50,000, initially high, some cleanup, some flow back, and we see our water rate, water oil ratio, and our GOR, started around, like I said, we did 280, and it's going down a bit. It's not jumping around too much. So maybe we're still above the bubble point pressure for our drawdown. We'd have to check, okay? And we have our tubing pressures here. Looks like there's a nice little buildup right there, okay? And our casing pressure is there as well. Now let's talk about gas lift for a second. So I'm going to turn on gas lift in the legend here. And it looks like initially there was no gas lift until maybe 40 days or so. And then we inject a little bit of gas lift. We're talking like 50,000 scuffs a day. And then they ramped it up to 350,000 scuffs a day for gas lift. And it's around the same today. Okay, so this well is on gas lift. And that's kind of the history of this well. All right, let's go down to bottom hole pressure right here. So we're going to look at this well's wellbore with this well data card, and we've got the square box right there. And click on that. Let me get my screen maximized up here. So we're going to click on this little well data card right here, and we see the deviation survey. This well, I think it's toe up. Yeah, it's toe up a little bit. If you look at the deviation survey, which is that little icon here above the table. And then we can click on well data on the top right, like that, okay? So on the left, we see configuration 1 and configuration 2. Often our well bores, the flow path will change. Maybe we go from casing flow to annular flow to tubing flow, or for an oil well, like this one, we just float up the tubing. And then later we do gas lift, or later we do an ESP, or later we do rod pump, things like that, okay? Speaking of like rod pump or plunger lift, if we pick these options, it will automatically use the quiet side pressure and any liquid levels that we've imported as part of the well history to calculate the bottom hole pressure. With plunger lift or rod pump, we've got this mechanical thing in the tubing, and that causes an issue to calculate the pressure to the perf. So instead, by default, we use the quiet side pressure if you ever pick rod pump or plunger lift. Okay, that's a bit of a tangent. But in this case, the well started with tubing flow. That's called configuration 1, right? No artificial lift. And then later, gas lift. occurred. Okay, so you can have as many of these configurations as you want. Typically, they'll automatically be imported for you through WellView or WellEase or wherever your wellbore descriptions are. Or if you want to add some sort of flow path change in the well's history, there's a little plus symbol in the bottom, and that will let you pick a date and describe what the flow path was. All right, so I want us to all click on configuration 2, and we see that artificial lift method is now under gas lift configuration. Let's look at this. There's a couple options. So poor boy is where we inject everything down to the end of tubing, and it all comes up to the end of tubing. It basically ignores any valves, and we say that we're getting gas lift all the way down to the end of tubing. Valves is the option we're going to use here, and if you click on valves, there's a little square box beside valves. Let's check that. Let's open up that box. In this case, we have the gas lift valve depths and the open and closed pressure. So these are PSO, pressure surface open, pressure surface closed, and these are used in the software to predict which valve has historically been open to inject gas lift at. It uses the casing pressure history, and then it looks at these open closed pressures and therefore figures out what depth has been open historically. Now, let's say that you have lots of valves, but you don't know where the details are. You don't have time to plug all those valve details in. A good option for you is automatic here under gas lift. So what automatic will do, it will take your historical tubing pressure, your historical casing pressure, and it'll figure out where in the wellbore do those pressures, and at that depth is where it will assume gas lift is occurring. Okay, and that can change through the well's history based on changes in tubing and casing pressure. So automatic is something we see people use a lot if they don't have time or access to all the valve details. All right. Reverse valves is basically reverse gas lift, where you're injecting down the tubing, production's coming up the annulus. Okay. So for today, we are going to use valves. Now, one thing I should mention for anyone who has ESPs, ESP, usually you have a pressure measurement, like a gauge pressure almost on the pump intake. Right? So if you were to pick ESP here as your artificial lift method, you want to use that pump intake pressure that you're measured at the pump. It's really important to enter your pump intake is at, right? So if your pump intake is here, let's say 7,000 feet, but your perforation is below at 8,000 feet, we're trying to calculate the pressure down here at the perforations to do this interpretation. So if your pump is here, you have to type in 7,000 feet, and the software will convert that pump intake pressure that you've imported like a gauge, and it'll convert it down to the pressure at the top perforation. So that's why it's important to enter this depth if you have an ESP. In our case, we're doing gas lift, valves, and we can either say save or X. We can get out of here. Sorry, before we do that, and if you closed out, let's go back in there. There's one little option we need to toggle on. Okay, so back in to our well data card. So there was a shut-in for this well, right? And we saw that the tubing pressure built up. What we want to do is we're going to be converting that surface buildup to a downhole buildup. To do that, there's a little gear wheel in the top here. So again, just to back up, we're in the well data card, click on the square box, find the gear wheel up here, okay? And there's an option that says compute, and the well is shut in. Okay, this is going to use the surface buildup to estimate the bottom hole pressure. So we'll say save, we'll basically toggle this on, say save, and we're ready to calculate our bottom hole pressures, all right? Here we have the results. Now, something Mo said earlier was, most operators have the daily rates and daily surface pressures automatically coming into Whitson through an API connection or Snowflake, typically an API connection. And so with that, you can schedule it so that the bottom hole pressures are calculated every night. For example, Devon has 5,000 wells connected into Whitson, and every night the new rates, surface pressures come in, the new bottom hole pressures are calculated. And so all the reservoir and production engineers are seeing the most up-to-date bottom hole pressures for all their wells every day. That's probably like one of the biggest bangs for your buck with Whitson, by the way. What we're seeing here are the bottom hole flowing pressures, and we see that there's a bit of a spread compared to the gas well. That's just because there's oil, there's water, there's gas, it's a mix, right? So the correlations start to spread apart in there. Now, which correlation are we going to pick? Well, we see that the green and the red one are pretty close to each other. In fact, this totally mimics the paper that I showed you, where Braggs and Brill would overpredict, Gray would underpredict, and Hagedorn and Brown and W&G, they were both within 5% of the gauge data. So this is kind of mirroring those results. I've been using Hagedorn and Brown and W&G, so let's use the W&G one again here, which will be the green one. All right, so that's the drop down that we picked at the top, W&G. Double click, zoom out, and we see the buildup here. calculated to bottom hole conditions, and then we rack on production. This is our bottom hole flowing pressure, okay? Liquid loading. So this is a very low GOR. You know what? Actually, I'm going to skip that. There's a little bug in there we need to work on, but this well is liquid loaded. We're not seeing the critical lift rate. Again, this is a little tweak we need to fix, but this is such a low GOR well. I'm not really worried about liquid loading. I know I need gas lift. So we're going to move on to this gas lift plot. Okay, there's a lot of stuff on this plot. The thing I really care about are these blue dots. So in the legend, I'm going to double click on gas lift valve depth. And if the double click isn't working for you, it just means that you need to click it even faster. Matthias says we need to work on how fast we are with our double tapping. So what we're seeing here are the valve depths that are predicted to have been open in the well's history. And this is all based on, and we can click on this little icon up here in the top part of the legend. We click on that, it gives us a reminder of what those valve depths were and the open close pressures. So based on the historical casing pressure, these are the gas lift valves that were open. So we started quite shallow. Later we got down to a deeper valve. There was a shut-in, and it looks like now we're down finally at the bottom valve. Okay, so this is pretty handy just to toggle through. You know, if we had lots of wells with this done, you could just click next, 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 and you could see this result. Okay, I'll just hit pause and see if there's any questions coming into the chat window here. What is when the model is referencing the casing pressure? Okay, so when the model is referencing the casing pressure to the closing pressure in the table, is the friction component subtracted? Okay, so in this case, the inputs for the gas lift valves are surface pressure conditions. So these inputs come from your gas lift valve supplier, and they're not considering friction or hydrostatic because it's a surface pressure input that is and I've looked at like at a wellbore diagram with these inputs, and they provide them typically. But you know, on that point, maybe we should consider an option where the downhole pressures are an input for the valves, and then we could potentially calculate that as well. So for now, we just input the surface pressure. Yeah, when I see Mo actually type the answer in there too. Okay. All right.
I had a quick question, Graham. This is Jessica Stieber. On your gas lift design, when you put it in there, it has the option for or if you go back to the like bottom hole pressure plot or the little pumping unit guy, right? It has the option to say if it's the flow path. So if you are doing annular gas lift, where you are injecting gas down the tubing and production is coming up the casing, can you just put your flow path as casing and still have your valves and everything, and then everything will work out, calculate correctly?
Yeah, so like I think you're asking if you have like reverse gas lift, how do you set that up?
Yeah, because before you just said reverse, but the flow path was still tubing, so I was kind of confused.
Yeah. So Mo can correct me, but I think there's actually two ways to set up reverse gas lift. Like one is like we've described here, and the other is you could say flow path is annulus, and then we would just call it.
It just calls it reverse valve, anyways.
And Mo,
Yeah.
you might have to.
That's correct. Yeah, that's a very, very good question there, Jessica. So basically, if you wanted to do reverse gas lift, the flow path is referring to kind of where you're flowing through, regardless of the gas lift, and that's basically you're going to be. If you're doing reverse, then the flow path should be the annulus. Then your artificial lift method should be gas lift, like shown here, and then the gas lift configuration, you see, you don't have the valves option anymore. It's just reversed valves that you have, and that's the one you should use. And we will consolidate those because we had reversed valves and we have reversed valves and valves now, but in the future we'll just have one option. It will be valves, and it will automatically know which one to pick based on your flow path, if it's annulus or if it's tubing.
Okay, and then one more question. Under the flow path option, it also has tubing and annulus. Why would you use this?
Well, some people will flow up the tubing and the annulus at the exact same time.
Yeah, that splits the flow basically between the tubing and the annulus there, so you can flow through both at the same time.
Yeah.
Perfect. Thank you, guys.
Yeah, not too common, but it happens. Yeah. Okay, so we're going to keep going, and our bottom hole pressure to be used, we're going to use the W and G1 here. Let's do our flowing material balance. And again, the goal here is to estimate the current reservoir pressure. All right. So under flow material balance, we'll click, and we've got to fix something for the scale here. I apologize for that, but you see way down at the bottom left, we see these blue data points. I want to zoom in on that. And the way I'm going to do that is I'm going to draw a box on my screen like this, and I'll let go. I'll just repeat that a few times until I see my data like that. And I'm going to repeat that in case anyone missed it. The data's a little squished in the bottom left, so I'm going to just draw a box around the bottom left corner until I zoom in, okay? So I want everyone to go ahead and try to move your black line around until you can try to find the most shallow slope that you can justify or that you can interpret here. And what we're doing here is, again, we're estimating the size of the reservoir, the fluids in place. And you'll see those results are on the left as you move your slope around. And once you think you've got a slope that you like, click run. Now what I'm seeing is my contacted gas in place is around 900. My contacted oil in place is around 2.3 million barrels of oil. And again, everyone's going to have a slightly different number. And I want to look at the reservoir pressure up here. So in the top right, I'll expand this pressure plot. Expand is in the top right. And so just to review, our black line is our average reservoir pressure, and the gray dots are the bottom hole flowing pressure. Now, all of this looks pretty normal, except after the well was shut in and turned back online, our bottom hole flowing pressure is higher than our average reservoir pressure. And that's not really possible. Our black line should always be above the trend of the gray dots. And so this kind of flush production we're getting after the shut-in, the bottom hole pressure is giving us a clue that maybe we need a higher reservoir pressure at that point in time. Well, how do we get that? How do we get that black line up? We need to make the reservoir a little bigger. So this is the beauty of any time that there's a shut-in or we get like some flush production, we calculate the bottom hole pressure again, it can potentially make the reservoir a little bigger. So the way we're going to do that is back on the flow material balance, I'm just going to lower the slope of my line a bit like this. All right. This is, again, everyone's going to have their own interpretation here. I've got it down so that my gas in place is around 1 BCF. My oil in place is around 3.9 million. Again, you can mess around with the slope of this line until you get in the ballpark, 3.9 million barrels of oil. And after you've done that, you'll click run. And then I'm going to go check out the pressure plot again. Now I'm seeing my average reservoir pressure went up a little bit because I made the reservoir bigger, my interpretation. And now for the most part, my black line is above the flowing pressure dots in gray. I've got like a little straggler up here, but I'm not too worried about that. It's really about like the trend. And I'm okay with this as far as the size of my tank and my remaining reservoir pressure. So again, if anyone's not getting a similar result, just try to change your slope here until you're around 3.9-ish million barrels of oil. Click run, and then we should see that our reservoir pressure is around 3,100 pounds, around there. Everyone's gonna have a little bit different answer.
Hey, Graham.
Yes.
Without build-up data here, our original pick was about 600 psi off of what we think the reservoir pressure is. So my concern is for wells that I do this interpretation on, that I don't have build-up data on. Am I off 600 psi on all those wells?
It could be. So one of the facts is like with these low permeability wells, we don't reach boundary dominated flow for years and years, right? And as a result, the volume that we're contacting is really the minimum volume of fluids, right? So like with this well, if this well was only on production for a month or so, the slope we would get would be something we'd only contact like this much, right? But with more and more time, we see farther out into the reservoir, and that causes the slope to go down. And so indeed, the volume and the pressure, the volume we're seeing here is like the minimum volume so far, based on how long the well's been producing, and therefore this reservoir pressure is really a minimum reservoir pressure and potentially low. There's a couple ideas we have to kind of make that fact a little more obvious and even bracket the range of reservoir pressures when you're not seeing the entire drainage area. So what you said is totally valid. Yeah. I guess on the other side of things, I see production engineers using the original reservoir pressure for IPR curves sometimes, which is often, an overestimate of the remaining pressure. So it's you kind of have to pick your poison, right? Which way do you want to go? Let's see here. As long as our current reservoir pressure is around the 3,100 pound mark on the black line.
Hey, sorry, on that quick question. Would a good way to sniff that out be like a productivity index plot, like a J plot, so you can see like a large jump or large dip over time?
Yeah, so I think if we were to plot like productivity index for this well, it would probably show a spike after we turn the well on again right here, right?
I'd have to graph it. But...
Yeah, I agree. But I think because like typically with low permeability wells, anytime you have like a shut-in or like a quick change in drawdown, the J value or the productivity will temporarily appear to spike for a second, and then over weeks or months it will hopefully stabilize again. That's been my observation, at least.
Yeah, because like when we get to the nodal screen, how I detect whether or not I need to go back and play with my reservoir pressures is if my productivity index is higher than normal, like crazy high or crazy low. Like that's kind of the indicator that I roll off of. I don't know if that's right or wrong way to go about it, but
no, there's nothing wrong with that. You know, the tough thing though is like these wells, the productivity of these wells, to say that it becomes totally flat and like stabilized, that may not happen for like years and years too, right? But I think what you're talking about is a good diagnosis. All right, so we are going to go down to nodal analysis down here in the bottom left, and the black dot is the most recent day of liquid rate and the most recent bottom hole flowing pressure, 1,700 pounds. You'll notice that the reservoir pressure here on the y-axis here, this is coming automatically from that flowing material balance result. So is anyone's red line not intercepting around 3,100 pounds? If it's not, we can figure that out. But we'll say create VLP. That's the blue button right here, and we should see our current operating point for the well. Now notice down on the bottom left it says gas lift rate 216. That's the current gas lift rate on this well. Now just as a quick check, let's change that to 500. So what we see is it looks like if on this well, if we were to increase the gas lift rate, we would go from 560 barrels a day of total fluid, we'd increase it by 100 barrels a day. So that's just a quick kind of deterministic check you could do. I want us to also change that back to 216 though. Okay, we're going to get back to our current conditions to 216 gas lift rate and create VLP. All right, we're going to come back to this more about the gas lift tuning. The thing I want to look at right now, though, is this thing called gradient. So up in the top left, or sorry, in the very top here, we're going to answer the question, how much of this pressure loss in the wellbore is from friction? How much is from hydrostatic effects? So the first thing we see here is it's automatically drawing the most recent rate and surface pressure from the well's history. And it's saying this is the current bottom hole pressure, 1,700 pounds. But what's more interesting is this line in the bottom left. So this is TVD on the y-axis and flowing pressure on the x-axis. So we have our wellhead pressure, which is 152 pounds in the tubing, and it's calculating the flowing pressure all the way down through the wellbore, all the way to the toe, basically here. Okay, so this is in TVD. But what about if we want to plot this in measure depth? Well, there's this little MD button right here, which we can click on, and that changes the shape. It looks weird now. So what we're seeing is the pressure at the tubing. Pressure goes up, 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 up. And then this is the heel. That's where the highest pressure is. And then as we go towards the toe, there's slightly less pressure. So I'll let anyone volunteer. Why do we have this shape? Why is there more pressure at the heel and less pressure at the toe?
Because the toe up well.
Exactly. This is a toe up well. And so, we've got the pressure here in the toe is this pressure here. And then as we go to the heel, there's a vertical drop. So there's gravity happening. So that's why the heel is right here, has the highest pressure. But if you ever see a weird looking shape like this, that's just why, right? We're toe up. Okay, so let's break this thing down into hydrostatic versus friction. So way over on the far right, where I am right here, there's a little 4 window looking pane. We can click on that, and this is breaking the wellbore down into pieces, right? Vertical chunks. And so there's a lot of stuff here. I don't want to look at all this stuff. And so there's a checkbox in the very top left, which we'll click on. And what I do want to show are depths. So I'll expand the depths triangle, the little pointer, and I want to do MD, measure depth. And I'll go expand pressure drops. And in there's something called friction cumulative drop and gravity. So now we're seeing on the bottom row, the total pressure drop from friction is only 62 pounds. And the total pressure drop from gravity or hydrostatic effects is 1,300 pounds. So we see what's really dominating the pressure drop in this well with the current rate that it's operating at. Okay, you could always copy these to your clipboard if you want to get them out to Excel right up here. Let's talk about this thing called the gas lift curve. All right, the whole idea of adding gas lift is to reduce the bottom hole flowing pressure. If we have this really heavy column of water or oil in the tubing, there's no gas lift. We usually have a very high bottom hole pressure. And so in this case, no gas lift on the x-axis, 0 for gas lift means a high bottom hole pressure. If we start to add a little bit of gas lift, hopefully that will lower our bottom hole pressure. It reduces the density of the fluid in the tubing, reduces the bottom hole pressure. That's good. add a little bit more gas lift, add a little bit more. And this is kind of like the holy grail. How do we get the bottom hole pressure as low as possible at some particular gas lift rate? But what happens if you keep adding more gas? You actually add, and because all that gas you're stuffing down has to come back up, and that can unfortunately increase your bottom hole pressure. And I'm going to show you guys a case study at the end of where that really happened and what did the operator do about it. We're trying to get to this low bottom hole pressure at some gas lift rate. So if you take all of these points and you want to apply them to like an IPR curve, what you end up with is this green line. So with this, you can say as you increase your gas lift rate, how can you increase your oil rate? And hopefully you can get to this theoretical peak liquid rate at some gas lift rate. Has anyone on the call been using a curve like this either in Whitson or in like Snap? I think Snap might have something like this as well. That's all right. I've seen. For me, this was new. I hadn't even seen this curve until a year ago, until someone showed it to me. So we're gonna use this right now. All right. Okay. So right here it says gas lift opt. We can click on that, and it should do this all by itself. Now everyone should be seeing a number in the bottom left that's around 100. And if for some reason you're not, especially if your number is lower than that, I just want you to go back to your IPR VLP tab here in the top and make sure that your current gas lift rate is 216 down here. That's what it really is for the well today. So it's gonna kind of reference that when we look at our gas lift curve. So what are we seeing here? Well, we're seeing that the current gas lift rate for this well is 216. That's what is on the x-axis, gas lift rate. And the current oil rate for the well is 440 barrels a day. That's what's on the y-axis. So this is where we are today. If we were to increase our gas lift rate, we would march up this line and we could theoretically increase it by about 100 barrels a day, but we'd have to inject almost 1 million cubic feet a day of gas. That's a lot of gas. Now, the other crazy thing is if we were to reduce our gas lift rate, on the y-axis, march it down here, the well would theoretically still produce 120 barrels a day of oil, even if we turn gas lift off completely. So it's really telling us the entire range of gas lift from 0 to 1 million plus and what the oil rate response is going to be. Okay, and this is where we are now. So, if someone looks at this, are they going to automatically go ahead and inject 1 million cubic feet a day for gas lift? Probably not, because we have the shape of this curve. We really have these diminishing returns, and economically, you might even be in the sweet spot right now. Maybe you can move it up a little bit, but again, this peak of this curve is just a theoretical maximum liquid rate. It just may not be economic. So how do we kind of represent these two? Like, we know our current case, right? We're kind of reflecting that on the IPR VLP. That's where we are here. But what if we wanted to recreate, this point and even this point with no gas lift over on the IPR VLP? Well, let's do that right now. So we'll go up here, IPR VLP. First, we're going to type in 950,000. That was kind of like the peak liquid rate we could theoretically get at that particular gas rate. So we'll type 950 and then create VLP. And I might save this case and I call it max oil via gas lift. Okay, and save that. And then I might turn gas lift off. I'll type in 0 and create that VLP. And I'll save it, no gas lift. These cases are saved below so you can kind of see them, right?
There's a couple of questions in the chat, Graham. We check those out.
So one of them is, how come the friction cumulative drop across the entire lateral length is basically 0? I didn't actually notice that, but you must have noticed it. It's probably, I'm going to quickly look at that here. Yeah, so we're seeing that the friction, so like it looks like most of the friction drop is in the first, 5,000 feet or so, vertically. And then below that, we're talking tiny fractions of a PSI along the lateral. And it's really just because the rate of this well, at that point, like the rate we're talking 400 barrels a day, low gas rate, low water rate, and a big cross-sectional area. So there's very little friction. We could always try different correlations and see if it impacts that. But that's actually the topic I want to investigate more. Like, if you guys don't follow our LinkedIn page, every day we post something usually educational, and I want to basically do a sensitivity on this where I do a whole bunch of predictions of pressure drop along the lateral with lots of different rates, lots of GORs, lots of pressures. So, but in this particular case, that's what we're predicting. Okay, does the gas lift optimization plot only does the gas lift optimization plot only calculate correctly for points in time that is flowing below the Turner critical rate? Okay, so for the gas lift curve, we don't really look at critical rates. I mean, this is a good point to mention too, is the pressure loss correlations like Beggs and Brill, Gray, all of those. they calculate bottom hole flowing pressures, but what they don't do is they don't necessarily account for Turner and Coleman. Like Turner and Coleman are totally separate and independent from pressure loss correlations. So what I mean is, if the well is predicted to liquid load according to Turner and Coleman, the bottom hole pressure prediction, it may not necessarily change. So like for these pressure loss correlations, there's these things called flow maps, and they use things like annular mist or slug flow or intermittent flow. These are like these labels for flow maps that each correlation has, but that's not related to Turner or Coleman. And so I guess I wanted to differentiate a pressure loss correlation against a velocity prediction. And Mo, you can correct me, but the gas lift curve doesn't really do anything related to critical lift rate.
Yeah, I think we had the point to where it highlights if you're below the part of the curve is below the critical lift rate, it would tell you that, and there you have the critical velocity correlation for that. So it would highlight it if you were below at some point, so that you know that you need to inject. And the main point with that is, okay, you can take the critical velocity correlations with a grain of salt. Of course, that's a separate topic. But the main thing with this is, okay, I'm giving you a gas lift rate that I think is optimal for you. Maybe this plot shows you that you should inject less. You don't need to inject that much, but the oil rate is not the whole part of the story. You might be injecting just because you want to go above the critical rate to lift. So this would show you that. It would show you, okay, if you reduce your gas lift rate, maybe you'll be fine. You'll have the same amount of oil, but you'll end up maybe loading the well. So that's why, if that was the case, it would show you that more specifically. And it would be, many people would argue it's more applicable for gas wells, but we still have it both for gas and oil wells if you would like to use it, because it was requested.
Now, Mo, I don't see any visual.
Probably outside of that, outside of the range for this case. Yeah.
Okay. Okay, cool. Maybe if we follow up, we'll include like a screenshot of that in action. Yeah.
Yep.
If I see a plot that has drawn essentially a straight line, no change, and we're talking about the gas lift curve, I think here, is there a common error that I've made somewhere? Here's a sample of what I'm seeing. Okay, and Mo is checking for you, so we'll get back to you on that.
Yeah, I'm checking that. I think what happens is the configuration is not gas lift, like the main configuration is not gas lift, so I'll fix that. Fix that for you, William, and let you know.
All right, so this is basically a snapshot of where we are today. And we see that if we were from the gas lift op curve, this is our theoretical peak liquid rate we could get through gas lift change. And if we turn gas lift off completely, this is what our liquid rate would be. So we're basically seeing the entire spectrum of rates available through a gas lift rate change. All right. Now, the next thing I'm going to do, I want you guys to watch. You don't necessarily have to follow along. Okay. So I'm gonna basically do I'm going to call it a grand look back. So with this, I'm going to recreate from the well's history a little bit earlier. So I'm going to go back to when the gas lift rate was a little bit lower. All right. So the gas lift rate, we're only around 30,000 gusts a day or so here for gas lift rate. So when I pick this vertical point, it's sampling the rate, the bottom hole flowing pressure there, and even the average reservoir pressure at that time, which was higher, 4,100 pounds, according to the flow material balance. This is these are my conditions back then when I had a low gas lift rate. And if I were to go to my gradient calculation at that point in time, I can go ahead and pick the same around here. And I see, I'll call it look. And I see way back then, my bottom hole flowing pressure was 1,000 pounds higher. And I'll change this to PVD. So this is today's bottom hole pressure, 1,700 pounds. Back in the day, we were 1,000 pounds higher, 2,700 pounds. All right. You know, why was that? Well, I'm kind of curious about that. So if I go into my little pressure drop thing here, I see that hydrostatic or gravity pressure drop back then was much higher, 2,200 pounds pressure loss just from gravity. Whereas today, it's only 1,300 pounds from gravity. What's so different between today and back then? Well, it's the gas lift rate. Okay. So we had very little gas lift back in the day. Now we have more, and that is really affecting the fluid in the tubing, and therefore what the gravity pressure drop is. So it's just nice to do these look backs sometime to see why was the pressure so high back then. All right, what about the gas lift curve way back then? All right, so this is when we were injecting only at 31,000 gas lift. Way down here on the curve, look at all the opportunity in liquid rate if we increased the gas lift rate, which it looks like they did. Right. So this is another use for scenarios, is to take little snapshots in time, and you can toggle between them and see what we were doing in the past, what we're doing today, and compare those things. OK. All right. So let's do one last little trick. And this is something that's pretty new in Whitson. It's really about how do we estimate the initial reservoir pressure from some early time data. All right. So for the same oil well, I want us all to go to bottom hole pressure. There's a little icon in the top right here. I put my cursor over it here, my mouse. It's beside the green check mark. It says estimate initial reservoir pressure. All right, so we can click on that button. Now what we're showing here are the first 10 days of production. And we have the what the oil rate was on the x-axis for the first 10 days and what the bottom hole flowing pressure was for the first 10 days. From this, there's a lasso, I don't know if you guys call lasso or lasso, but there's this little icon up here. We'll click on that and I'm going to draw a circle around all of these green data points like this, and then I'm going to let go. And what the idea here is this straight line is going to point back at what could be the well's initial reservoir pressure. You know, some of the traditional ways to get initial reservoir pressure could be like a DFIT or some sort of gradient calculation, but this is actually using just some early time, really early time production data to try to point back at what that initial pressure was. All right. And this works for gas wells as well, but this happens to be an oil well. Now, if I were to zoom out, look at the shape of this curve, hey, look, it's an IPR curve. So that's kind of the theory behind this. Is it's just a quick way to try to estimate initial reservoir pressure from very early time production and flowing pressure data. Well, guys, the course is almost over. The last thing I was going to do is just give you guys a preview about where we're going in the future, because this nodal analysis stuff, it's only about a year old or so in the Whitson software, and we're really just barely dipping our toes in the water. There's so much more coming based on your feedback. But before I give you a preview of that, I just want to make sure I can answer any remaining.
Whenever you're doing like gas lift looks, if you change the casing pressure, you know, that theoretically should change the gas lift valve injection depth, which you can't really do. Like, it just does what it does, but in real life. But like, does that actually affect the VLPs? Because I've done it before and it seems like it doesn't affect it that much.
Yeah, great question. So for the well we've been looking at here, like I'm going to go and look at the bottom hole pressure tab and gas lift plot. And this is saying, like, for this particular well, it's saying that today we're on the bottom valve based on the open close pressures, based on the casing pressure, right? So, you know, how does that actually affect our VLP here, you know, for example? So if we were to increase this casing pressure to, like, I'll just say 1,100 pounds and say create VLP, you'll notice that it's predicting a lower bottom hole pressure. Sorry, it's predicting a higher bottom hole pressure and a lower liquid rate at a higher casing pressure, according to the.
You'll be injecting on a shallow.
Yes, exactly. You're injecting at a higher valve, and so it's predicting a lower.
Yeah. Okay. I guess that is what I would expect. I think when I've done it before, I did not see that little shift, but maybe I did something wrong.
It can really just be the threshold of the valve inputs and what pressure you typed in.
Yeah, exactly. It could be that. It could be also if your injection rate is not having a significant, if your gas lift injection is not having a significant effect on the VLP anyways, regardless of where you inject, it's not going to have a big effect. So there's many reasons why they could look the same or very much the same, but definitely the software should be accounting for the change in casing pressure as long as the configuration is valves with multiple valves.
Yeah, exactly. If for some reason, just double check you have all these inputs set up, you know, so it uses them too. Yeah. I want to expand on that topic a little bit, because if we were to go to our gas lift op curve, this curve it's basically using one valve based on whatever the casing pressure is, like in this row, like this little modified case thing. It's got casing pressure, and this input is using the current casing pressure from the well's history, and that's dictating which valve is open. But you could do sensitivities where you put in, like, you know, lower casing pressures or higher casing pressures, and it will predict which valve is open. And what does that really look like as a result? Well, it looks like this. I've drawn this little, you know, wellbore to give us a reference. So if we have a very high casing pressure, we're only injecting in, like, the top valve. This is what our gas lift curve would look like, meaning, you know, this is the maximum oil rate we could get right here. This is where we are today. You know, there's not a lot of opportunity. But if we could get down to a lower valve, then we can access these other gas lift curves, which, you know, even keeping the gas lift rate the same, which is where we're on the x-axis, we could still increase our oil rate by getting deeper, or increase our oil rate by changing the gas lift rate, shifting on the x-axis over to the right. So this is a very busy picture, but it kind of summarizes that there's two ways to increase our liquid rate, either through a gas lift rate change or through getting deeper.
This exact question was on my mind also. So
yeah, so I created this in Whitson using that gas lift, and you can you don't have to lose. You can basically just make lots of rows here with different casing pressures, and it will make those curves all on top of each other here. I want to talk about over injecting real quick. Okay, so this is a well started 800 barrels a day. We're down to 200 barrels a day. Lots of gas naturally from the reservoir. 4.5 million down to 2 million, and our GOR was 5,000. Now we're up to 7,000. This well was on gas lift, so the gas lift rate was very high, 1 million cubic feet a day, down to 700,000 a day. Still pretty high. Now their goal was to avoid liquid loading. So this is the reservoir gas rate. This is the critical lift rate. So we're not liquid loaded. Maybe we're getting close, but not really. But then on top of that, they had reservoir gas plus gas lift. Okay, so the dark red line is the combination of reservoir plus gas lift, which is give you an additional wedge, an additional safety factor above liquid loading. But I didn't really think they needed it, right? They had enough reservoir gas. Looking at this, like, on the IPR VLP, this is where they're operating, and we're looking at this as bottom pressure versus like liquid. But you can also look at this as a gas IPR. Why not, right? We're producing both gas and oil, so this is the same thing, but same well. But just looking at it from the gas perspective, and we are not liquid loaded, right? This is our critical lift rate. This is where we are now. No worries about liquid loading. What does the gas lift curve look like? This is where we're operating now. This is the theoretical peak liquid rate. So this is, if you ever see this where your current operating point is to the right of the peak rate, means you're over injecting gas lift. Now, something important here is look at the scale on the y-axis. Like this line is actually quite flat, quite horizontal, but I'm zoomed in. So from the bottom is 193 barrels a day, 194 barrels a day. So this whole y-axis is 1 barrel a day. So this line is basically flat. So even if they turn gas lift off, they're going to maintain their oil rate. So this is just a case where we were over injecting. So after looking at this, we decided, well, I think we could even dial down gas lift or maybe even turn it off, and we might not even lose any liquid rate. So this is when the gas lift rate was high, 700,000 a day, and they had 200 barrels a day of oil, and they turned gas lift down to zero. Gas lift was shut off. This is a real case. Just a month ago. Here's what the oil rate did. All right, it temporarily jumped up to 400 barrels a day, stabilized. So clarify what's going on is all that gas lift that's being injected, all it's doing is adding friction, reducing the hydrostatic load in the tubing. So that was a good response in the field. And what about the gas rate? So it was originally 2.2 million a day of reservoir gas. They turned off gas lift, and the gas rate from the reservoir doubled, and it's kind of staying there. Okay, so that was another positive response. But as more time went on, the field guys noticed that the temperature in the tubing dropped, and they thought liquid loading was happening. So they turned gas lift back on, and then the guys back at the office said, no, turn it back off. So they did. And then the field guys turned gas lift back on. So there's just been some back and forth with the field about keeping the gas lift off. But overall, it all started with realizing this in Whitson, that this was over injecting was going on, and then making an action in the field to turn it off, and then observing the positive rate response. Plus, they were able to sell the gas lift gas down the pipeline. So this operator I was talking with, they were not the only one who I've seen this at. Like there's been more than one company where I've seen they're operating way over here. They're over injecting, and a lot of people often have a hunch about that, but it's good to have this sort of physics-based way to back it up and then make the change in the field. Now, to take the pressure off anyone who might think this is happening, the reason it's happening is when the well is young, the GOR can be very low, and when the well is young, gas lift is needed. But over time, the GOR from the reservoir will often just increase naturally, and that natural gas coming out of the reservoir is acting like gas lift, and it's creating the same effect as gas lift. And so it can be worth it to go do a look back and see if you're potentially over injecting, and that's an opportunity to dial it back or maybe even turn it off. For this particular operator, they're now looking at all of their wells for similar opportunities. Okay. I guess I'll hit pause and just ask, does anyone else think they might have some wells that are being over injected for gas lift?
I mean, I guess
Definitely.
you showed GOR there. Sorry, but shouldn't it be GLR? I mean, water is a pretty big factor there.
You're totally right. Gas liquid ratio would be a more complete way to account for the liquids. So this would be another screening tool to plot GLR versus time, and you might learn that there's some sort of threshold that guides you to turn gas lift off before you even do this full analysis. Okay, so what is coming down the road? Well, for liquid loading, we looked at one well at a time, and we looked at the critical rate and actual rate, but that's not the most efficient way to do it. So we're almost done the development is more of a screening tool where you can look at all the wells and report, are they unloaded? Are they loaded? But not only for today, but basically type in like how many days do you want to look back and take the average, 20 days, 30 days, 40 days, because you may have some ups and downs in your production. So this is going to be more of a screening tool for gas wells, right? To see if they're liquid loaded. And later we're going to have hopefully this on like a GIS map with a bubble map and all this stuff. But the immediate thing will be a table to screen liquid loaded wells, right? That is naturally going to evolve into something similar for gas lift, right? Where we have this oil rate that we might be leaving on the table. And the idea is to basically batch run this on all wells and this to automate this process, right? Automate the IPR, automate the gas lift curve, and report the wedge of oil rate that we're leaving on the table, and then rank it, right? See which wells have the biggest opportunity for a gas lift rate change in terms of what their liquid rate will respond with, right? So that's going to be coming pretty soon. It's going to go hand in hand with that liquid loading sort of table. And then it's all about how do we distribute our gas lift to yield the maximum liquid response. So imagine that you've only got 5 million a day of gas lift. Which wells a particular amount of gas lift to yield the biggest rate response? And so every well's going to have its own little gas lift curve, right? That'll be done automatically. And then we're going to figure out a way to automatically the ideal gas lift rate for each well with the goal of the biggest total liquid response. All right. So we're not talking about like a pipeline hydraulic simulator. This is really going to be from like the wellhead. Hopefully this will provide some relief for people who do this kind of in an iterative way right now. Is anyone crying with joy, or is this not relevant?
Oh, this is great.
Good.
Totally
I'm
awesome.
Okay. Wicked. Good. Hopefully we'll give you guys a better timeline once we get some of these other things that have to happen first, like batch running these things. The next thing we're working on is future IPR curves. IPR curves, they were originally built for boundary dominated flow or conventional wells, and that's where they work, right? But in unconventional wells, the productivity of the well is changing for years and years, and so the IPR curve is changing as well into the future. So the really like complicated way to make a future IPR curve would be to make like a numerical reservoir simulator. We're trying to avoid that. So there's this idea where you can kind of forecast future reservoir pressure, forecast well productivity, and from that directly make a future IPR. So we're going to investigate this a little bit more, but the nice thing about it is it can be automated and it doesn't require a reservoir model. So we're going to look at that. The next thing, of course, too, with that is, an IPR, it's just a moment in time. But if we're going to do an ESP or gas lift change, it would be nice to make a forecast that reflects the change in the wellbore, right? Not just a moment in time. And so a lot of your reservoir engineers at your company have already made a reservoir model, like a history match for the well. And it's really just a matter of forecasting that reservoir model using different wellbore constraints. And so this is something we're going to be working on for liquid wells like this one, and also for gas wells in terms of predicting future liquid loading. Like when will it happen? Not just at what rate, but when will liquid loading happen? And can I schedule tubing change? Can I schedule things like that. So lots coming there. Now after the course today, again, I want you guys to think about this as an intro. I don't expect you to be like professional Whitson users after today. So just keep in mind, me and all the other Whitson people are available at support@whitson.com. Send us a note. And the help file is here. Oh, I should have shown you. The way you get in the help file is up on the top right, there's a question mark right here. And if you click on that, it'll actually take you to that exact related place in the help file based on where you were in the software just a moment before, right? So there's a bunch of stuff in here. There's that nice little picture. If anyone here wants to learn about like RTA, for example, we have these things called certifications. And so we'll give you 3 wells to analyze. We walk you through every single step, importing PVT, bottom hole pressures, the whole RTA workflow. You'll send us the results, and then we'll give you some thumbs up, a few tips. If you want to do any decline or type well work, we have the same thing. And then that Nodal certification, which is very similar to what we just did today, but you can follow it at your own pace. It's available here. So again, in the help file, question mark up in the top right, and then certification. And those are some good tips there. Okay, last resources to wrap up with is we have some online conferences, and we have an in-person conference. So the online conferences happen every quarter, and they're basically operators just like you giving case studies, and we record them. So these are all the case studies. You guys have access to them Some of them are about like nodal analysis here from Devin, to ESP or to not, that is the question. So if you see any of these recordings that you like, you can just click on it and check it out. We'll include this in the follow-up. And then if we just had our actual big annual conference in Houston 2 weeks ago called WhitCon, and we'll send the recordings out to you guys real soon. We're just getting them chapterized. But was anyone at WhitCon 2 weeks ago, or did anyone join virtually? I'm sure some people did. Yeah, so if you can make it, it's always in Houston. It's usually it's in September every year typically. So we'll make sure you guys all get an invitation to the next one, and also the quarterly online ones that happen as well. So with that, I just want to give everyone a big thank you for hanging in there. And again, we're just getting into nodal analysis, but the goal is to keep it really easy and always keep it improving. So now we have the awkward silence. I'm gonna pause the recording here.